always complete plan, complete contingency plan, right? So which means that whenever we talk about strategy or strategy profile, we have to think about all nodes, even if we know that that node is never weak. Okay? So strategy profile and strategy profile have to specify all of them. However, if I ask you what is the equilibrium outcome can be described more quickly, right? Because if I ask what is really the outcome of the game in equilibrium, then the outcome is simply player 1 chooses S, and that's it. So everything relevant, all other sub-games, they are never realized, right? So if I ask you what is the outcome, then it is player 1 choosing S, and the game ends. Okay? So maybe I didn't really emphasize that sufficiently, but it's kind of, it's not really, it's kind of straightforward, right? Distinction between equilibrium outcome and equilibrium strategy profile. Okay? And then whenever I ask what is sub-game property equilibrium, without any, other, if I just simply ask what is equilibrium sub-game property equilibrium, then what I really want to hear is, your answer should be equilibrium strategy profile. Okay? So the reason is that, so again, let me explain with example again. Let's say, okay, so we have equilibrium strategy profile such that all player chooses S. Okay? And let's talk about alternative. Namely, all player chooses S, but player 2 chooses C here. Okay? So we are comparing two strategy profiles. The first strategy profile chooses S all the time. And in the second strategy profile, all players chooses S, except that player 2 will choose C at the last sub-game. Okay? And if you compare what is outcome of play of those two strategy profiles, actually both of them result in the same outcome, right? Player 1, in both cases, player 1 chooses S and then the game ends. However, strategy profile, the first strategy profile is sub-game property equilibrium because it is Nash equilibrium in all sub-games. But the second strategy profile is not a sub-game property equilibrium because player 2 chooses C here, which is clearly not a Nash equilibrium for the last sub-game. Okay? So if you are asked what is sub-game property equilibrium, you have to report equilibrium strategy profile because there are tons of different non-equilibrium strategy profile which result in the same outcome. Okay, so the correct complete answer has to specify all strategy profile. I mean all player strategies and all nodes in the tree, and also explains why this strategy profile is Nash equilibrium for all sub-game. Okay, so that's probably one of the important point we discussed. Okay, so we also so there is also a nice property of sub-game property equilibrium. I didn't really emphasize it last time. Okay, so in this case, there is unique sub-game property equilibrium. So everyone chooses S. But let's think about this sub-game. Okay, so let's think about the case that the game begins here. Okay, so then if I ask what is the sub-game property equilibrium for that game, which begins here instead of here, then it is the sub-game property equilibrium for the entire game remains to be sub-game property equilibrium. Okay, so that's another nice property of sub-game property equilibrium. If you restrict your attention on smaller part of the game, then we can also ask what is sub-game property equilibrium if that small part is the entire game actually, then the answer does not really change. Okay, so you simply restrict the sub-game property equilibrium for the entire game to that sub part of the game, then still that is subgame property. Okay, so we also talk about backward induction and one-shot deviation principle. Not gonna really want to repeat this again. So one-shot deviation principle basically says that you only have to check one-shot deviations if you want to prove a certain strategy profile is whether it is subgame property equilibrium or not. So it's not really this kind of trick that can simplify your life, save your effort and time whenever you solve some questions or the exam or problem set. Okay, so it's kind of useful technique. One-shot deviation principle. And probably the other important thing is sequential rationality. I mean, in terms of rationality, we have to assume if we want to use subgame property equilibrium as our equilibrium concept, actually we need not only rationality but also sequential rationality. So rationality and sequential rationality is kind of similar but actually different. Rationality, so sequential rationality means that on the top of rationality, mere rationality, sequential rationality means that players have to rational after any history of the game. Okay, and that's the reason in subgame property equilibrium, whenever we restrict our attention to a certain subgame, our candidate of equilibrium have to subgame equilibrium in that subgame as well. Okay. Okay, so a lot of things. I mean, we kind of spent 2 weeks to discuss subgame property equilibrium, so I don't really want to go over any further details anymore. So if you have any questions about subgame property equilibrium, you can come to my office hour, or we're gonna schedule another review session very soon. Probably the next week. I'm gonna post the announcement very soon. So you can also come to the review session if you have anything unclear about the notion of subgame property. Okay, so and then in the I think we have to wait a little bit. So and then in the second half of the last week, we applied our notion of subgame property equilibrium to the bargaining problem. Okay? So what is the bargaining problem? So bargaining problem means any situation such that 2 players, I mean, it is not necessarily 2 players. We can think about bargaining situation with more than 2 players, but let's focus on the case with 2 people, 2 persons only. So bargaining situation means, or more precisely, 2-person bargaining situation means that any situation such that 2 players have to decide how to divide the surplus on the table. Okay, so for example, price negotiation is just good example of bargaining problem. There is buyer and a seller, and both of them understand there is gain from trading. Okay, so the buyer attach higher value to the good than the seller, so that makes the gain of trading strictly positive. So which also means that they know that so they understand there is certain surplus they can generate together, and the problem is how to divide that generated surplus between buyer and seller, right? So that's the problem of price negotiation. So that is just one good example of bargaining problem. And we are mostly focused on that kind of bargaining problem, price negotiation. But I also mentioned last time that actually the same mathematical structure can be observed in many other cases, such as intra-house bargaining, bargaining between husband and wife, and also political bargaining, bargaining between 2 different political parties or 2 different politicians. Okay? Okay, so there can be hundreds of bargaining situations you can study with game theory, but I already mentioned that we are gonna mostly focus on the case with two players, okay? And also we focus on the case that there is no uncertainty about the surplus, the size of the cake on the table they have to divide, okay? This is this is one assumption we can make, but sometimes in real world, sometimes this assumption does not really hold. For example, you can think of the case that the value of the good, the buyer's value of the good is the buyer's private information, right? I go to coffee place to get some coffee, then sometimes, mostly not, but sometimes we can think of the situation that I have to negotiate price of coffee, right? Then in that case, the size of surplus we have to negotiate over is, that is determined by my valuation of the coffee, right? But sometimes it is reasonable that the other guy, the seller, does not know what it is, what is my value, right? So I don't really mean that kind of situation is uninteresting or unrealistic, but in order to analyze that kind of situation, we have to study how to analyze asymmetry information, right? That is something we have not done yet. So actually, I plan to talk about that kind of bargaining situation later on toward the end of the semester. But for now, we focus on a rather simpler case such that my value, the buyer's value of the good, is also known to the seller. Okay? Okay, so that is second simplification. So we focus on two-person case, and we also focus on the case where there is no asymmetric information. And there is actually third assumption, we maintain all the time. Okay, so there can be a lot of different rule of negotiation, right? Who can offer and who can counter offer, and when I can counter offer, etc., etc. Okay, simply there is hundreds, billions ways to negotiation, but here in this lecture we focus on probably the most natural case, such that two people alternate with each other, I offer first, and then it is rejected, the other guy offer next, etc., in alternating order. Okay? So it is probably probably the most natural bargaining rule, but not necessarily the only bargaining rule. Okay? But here we focus on the most natural case. Okay? So there are three assumptions we implicitly maintain all the time. Okay, so eventually what we want to solve is the negotiation problem such that eventually what we want to solve is T period alternating over bargaining game. What does it mean? So T period means that there are T periods, okay? So obviously, there are T periods, and where capital T is some number, okay? And so bargaining has to be over within T periods. And the way they negotiate over this T period is just alternating over bargaining. So the bargaining procedure I just described. In the first period, player 1 offers, and then player 2 accept or reject. And if player 2 accept, then the game ends. Otherwise, if player 2 reject, then the game moves on to the second period. And now, they alternate, they change their role with each other. So now player 2 offers, and then player 1 accept or reject. And if player 1 rejects, then they move on to the third period. Now it is player 1 who can make an offer, and then player 2 accept or reject. So they have to, they repeat that process all the way to period T. And if they fail to reach any agreement until the end of period T, then the game ends without any payoff. Okay? So if T is very large, probably this is kind of relevant some kind of realistic bargaining model. Okay, so eventually, what we want to solve this kind of problem. And also, so this kind of bargaining model is very realistic and relevant to the real world bargaining situation with some deadline. Right? So the bargaining has to be over within T periods. You can interpret that as two players having some deadline before which they have to reach an agreement. Okay? So for example, if it is price negotiation for a flight ticket, for example, then flight tickets, no one really negotiate for flight ticket, but just think about hypothetically, let's say you have to negotiate with some airline about to decide what is price of price ticket, then in that case clearly there is some deadline, right? I mean, your plan is you fly to US, for example, in next Monday, then price negotiation has to be finished before that deadline. And or if you think about application of political bargaining, then there is some in many cases there is also clear deadline. There is some deadline before which two parties have to decide whether they pass the bill or not, right? So that's another thing. And in many cases we have deadline, and for any bargaining situation with deadline, we can apply this model to analyze, game theory, to do some game theoretic analysis for that bargaining situation. But sometimes, there is also bargaining situations without deadline, right? So coming back to our earlier example of negotiation for price of coffee in coffee place, then it is difficult to think there is any deadline for that price negotiation. So for that case, we can also think of we will also talk about the case such that T is infinite. Okay, so T is infinite means that two players repeat the same problem, same procedure, alternating offer bargaining game forever until they reach any agreement. Okay, but this will come later today's lecture. So we will first focus on this case, finite T case. Okay, so how to solve this problem? We already kind of discussed a little bit about how to solve this problem. Okay, so we can actually solve this problem with backward induction. Okay, so there should be so there are many sub games here, but we can begin with what happens at the very last moment, period T, if they fail to reach any agreement until they fail to reach any agreement previously. Okay, so we can think of the case. Okay, so such that both players they fail to reach any agreement in period 1, 2, 3, 4 up to period T minus 1. So they simply fail to reach any agreement so far, and they just move on to they just entered the period T. Okay, so that is just one sub game, kind of actually the last sub game we can think of within this entire game. Then if you think about what happens in that last sub game, then that game is actually just ultimatum bargaining game. Right? So let's say in the last sub game, it is player 1's turn to make an offer. Then player 1 makes an offer, and then player 2 accept or reject. And if player 2 rejects, then the game ends without any payoff. And if player 2 accepts, then player 1 gets his own offer, and then player 2 gets 1 minus player 1's offer. That's what happens when player 2 accepts. And that is exactly the ultimatum bargaining game we discussed previously. Okay? And then we know that there is unique subgame property equilibrium for the ultimatum bargaining game. And in that unique equilibrium, player 1 offers 1. Here by offer 1, that means player 1 suggests I'm going to take the entire surplus. Okay? And then player 2 will accept. Okay? That's the equilibrium outcome of the unique subgame property equilibrium of ultimatum bargaining game. Okay? So we know that in any subgame property equilibrium, how two players have to play if they reach to period t. The last proposer will take the entire surplus. Okay? And then given that, we can go backward as always. So let's think about what happens in period t minus 1. Okay? Then it is now, okay, so now in period t, player 1 proposes, right? Makes an offer. So in period t minus 1, it is now player 2's turn to make an offer. Okay? And then let's say player 2, and if player 2 makes an offer and player 1 accepts, then the game ends. Right? However, if player 2's offer is rejected, they have to move on to the next period. Right? But we already know what happens in the next period. Okay? And then if you think about that situation, the situation in period t minus 1, that situation is exactly equivalent to the situation of ultimatum bargaining game with arbitration. Right? So what is ultimatum bargaining game with arbitration? So that is ultimatum bargaining game, except that if they fail to reach any agreement, then player 1 and player 2 get some payoff, some kind of outside option, right? And whatever happens in the next period is outside option for two players in the perspective of in period t minus 1, right? So then using that technique, we can also, and in that game, ultimatum bargaining game with arbitration, we also know that there is unique subgame property equilibrium, right? So that fixes what happens in period t minus 1 and period t if they fail to reach any agreement previously. Okay? Then you can repeat the same argument again. Then you can think about what happens if in period t minus 2. Okay? Then there is another ultimatum bargaining game with arbitration process. And then you can apply the same logic again to show that there is unique subgame property equilibrium for that subgame. And then you can reiterate that reasoning again and again until you reach the first period. And that will show that there is actually unique subgame property equilibrium. And in that unique subgame property equilibrium, player 1 makes an offer, and then player 2 accepts immediately. Okay, because because player 2 always accepts player 1's offer in ultimatum bargaining game with arbitration. Okay, so that's how to solve t period ultimatum offer bargaining game. Any questions so far? Okay, so I just described how to tackle this problem, just general trick for solving this problem, and that discussion of that trick also proves that there should be unique subgame property equilibrium, and then the negotiation process has to be completed in the first period. Okay? And what is really actual equilibrium settlement, what is really equilibrium outcome, what is the offer player 1 makes in the first period, is kind of different question. Calculation of exact equilibrium outcome is kind of can be complicated, but in principle you can calculate that thing as well with backward induction. Okay? So this is actually general proposition about the alternating offer bargaining game. So suppose t is any number. So here we consider the case t is any number. So if t is 1, then this is ultimatum bargaining game. Okay? Then for any t period alternating offer bargaining game, there is only one subgame perfect equilibrium. So there is unique subgame perfect equilibrium. And in that unique subgame perfect equilibrium, what happens is, the equilibrium outcome is two players make the following agreement in the first period. Player 1, the proposer in the first period, and player 2 obtains. So this is the offer of the player 1 in the first period, which is accepted in equilibrium. So this is the share for the player 1, and this is simply 1 minus the other one. So this is the share of the other player. So for example, let's think about the case such that t is 1. So that is the ultimatum bargaining game, right? So if you plug t equal to 1 here, then this term becomes 1, right? So t minus 1, the exponent will be 0. So if the exponent is 0, then the number is always 1, right? I mean something. Yeah. So if t minus 1 is 0, which is the case if t is 1, so this term is 1. So and the second term delta to the capital T, that is simply delta, right? So the numerator here is simply 1 plus delta, and denominator is 1 plus delta. So this is 1. And you can check by yourself, this is actually 0. So which is the case really, right? I mean, we ultimatum bargaining game, we know that player 1 takes the entire pie. Okay? So this proposition is indeed true for t equal to 1. What if t is 2? Then we have 1 plus, now this is minus 1 to the 1. So the entire thing here is minus 1. Delta square, right? So if t is 2, then player 1's payoff is 1 plus minus 1 squared, delta squared divided by 1 plus delta, which is 1 plus delta squared divided by 1 plus delta, and u2 is delta minus 1. If t is, it has to be 1, right? So if t is 2, then here t minus 1 is 1, right? Sorry, it was my mistake. So we actually have this. And here delta minus minus 1 to the t minus 1, which is 1. So this is just minus 1. Delta squared divided by 1 plus delta, which is delta plus delta squared 1 plus. Okay? So you can just plug any number t, then it gives you what is the equilibrium of. Okay, so how to solve this proposition? How to prove this proposition? No, we can prove this proposition by backward induction. I'm sorry, backward induction and mathematical induction. Okay, so what is mathematical induction? No. So here you can prove this proposition with t equal to 1 first, right? So we already actually proved that case, because that is simply ultimatum bargaining game. So in ultimatum bargaining game, there is unique subgame perfect equilibrium, and player 1 takes the entire pie. So you can check this proposition is already true for t is equal to 1. Okay? Then, is true for t is equal to 1. So this okay, so this is what we already know. So here I describe what is mathematical induction you have to use to prove this proposition. So first we already know proposition is true for t is equal to 1. Then prove, so this is something you have to prove. So prove that, I'm sorry, not prove. So assume, I'm sorry, so assume that proposition is true for t is equal to k, where k is some number. And then, so this is assumption. And then, using that assumption, and based on this assumption, prove that the proposition is true for t is k plus 1. Okay? So if you can do that, so the first thing here, proposition is true for t is equal to 1. So that is something we already know, right? So you don't really have to prove that again. So this is something is already given to us. And then in the second step here, what we do is we assume the proposition is true for t is equal to k, where k is any number, any arbitrary chosen number. And then based on this assumption, prove that the proposition is true for t equal k plus 1. And if you can prove that, so what happens? What is the result? What we can get is, okay, so we know that the proposition is true for t is equal to 1. Right? And then by the second thing here, we prove in the second step here, we immediately can see that the proposition is also true for t equal to 2. Right? And then that immediately tells you that the proposition is also true for the case that t is equal to 3, because it is true for the case with t equal to 2. Right? So, and that shows that actually the proposition has to be true for any t, any number. Okay? And how to solve this, the second part here? So you can do this second step here using backward induction. Right? So think about the alternating bargaining game with t equal k plus 1. Okay? Then, if two players fail to reach any agreement, then the game moves on to the second period, right? And whatever happens in the second period is just another alternating offer bargaining game with t equal to k, right? And we assume that the proposition is true for that subgame, and that tells us that what is the outcome if they fail to reach an agreement in the first period, right? So using that observation, you can transform the entire game into the ultimatum bargaining game with arbitration, and then you can solve what is the equation for that game, and that will prove the second part here. Okay? So this is the way to solve this, prove this proposition. Okay, so any questions? Okay, so we discussed two things. You can basically, effectively just at the end of the day, just one thing. So basically, we can solve any bargaining problem as long as t is finite. with backward induction. Okay? And using a little bit of more math, you can also prove this general statement for any possible t using the procedure I described on the board. Okay? I didn't give any details actually, how to exactly solve and prove this thing, but actually you can check the supplementary note I uploaded last week, on the canvas. So there is folder named by supplementary notes, and inside that folder you can find out the document titled by bargaining. Okay, so that is, I don't remember, kind of 15 pages article, 15 pages report document. And if you open that document, actually I describe all the details of how to solve, how to prove this proposition. Okay. Okay, any question? Okay, so then the next thing is, okay, so we have kind of got an answer, complete answer for the case with any t finite. Okay, so this proposition answers what happens in any alternating over bargaining game, as long as the number of periods is finite. Okay, and we, as already discussed, that game is just good model for the bargaining, any bargaining situation with deadline, right? But sometimes we don't have such a deadline in the real world. Then we have to consider, we also have to consider the case with t being infinite. Okay, so the game never ends unless they reach any agreement between two parties. Okay, so what is infinite horizon alternating over bargaining game? So as let's say that player 1 offers in odd periods. So player 1 offers in period 1, 3, 5, 7, 9, 11, etc. And player 2 offers in even periods 2, 4, 6, 8, 10, etc. Okay, and the rule of the game is basically same as before. Player 1 makes an offer, and then player 2 accept or reject. If player 2 rejects, then game moves on to the next period, and then player 2 makes an offer, etc. And what is the only difference is that the game never ends unless they reach any agreement. Okay, so the first thing you have to understand here is we can use the trick of backward induction. Backward induction is not feasible. Why?
W1, who is the last proposal?
So what is backward induction? Backward induction is basically the trick such that you look at the final moment of the game first and analyze what happens there and then move backward, right? But in this case, there is no final moment. The game is continued forever, right? So there is no single final period you can begin with. Okay, so the backward induction is not feasible. And that also means that we are not really sure whether there is unique subgame perfect equilibrium or not. Okay? So in the case, for the case with finite t, we could show that there is unique subgame equilibrium by backward induction, basically. But here we cannot really use backward induction. That also means that we are not sure whether there is only one subgame perfect equilibrium, or two subgame perfect equilibria, or to the worst case, possibly we can have infinitely many subgame perfect equilibria. Okay? So uniqueness of subgame perfect equilibrium is also something we can never be sure about. Okay, so then how to solve this problem? So this analysis of infinite horizon bargaining game